Good afternoon. Let positivity and knowledge. Good afternoon once again to all present here. Dear students, I am happy you have gathered here for the technology talk conducted by the Department of Electronics and Communication Engineering on satellite sensors and its applications. It is a great honor and privilege to have a very distinguished scientist, Kalpana Arvind, Associate Director, retired from ISRO, Bangalore. Before we start the event, I request everyone to kindly stand for the invocation. Kindly be seated. As you all be aware that this month, the month of August, was a month where the Indian Space Research Organization was started by Dr. Vikram Sarabhai. And in this very same month, we had our Chandrayaan landing on Moon, which is commemorated as the National Space Day. And in the middle of such memorable days, our university is really proud to have in space promotions director Dr. Vinod Kumar a few days ago. And today we are very happy to have another important scientist from ISRO, Ms.Kalpana Arvind, to share her knowledge on satellite sensors. May I now request our chief guest and Dr. Viswanathan, our rector, kindly take your seat on the dais, please. Students, please settle down. May I now request our rector, Dr. Viswanathan, to kindly share a few words to this gathering.
Good afternoon to all of you. Distinguished chief guest of this program, Technology Talk, Ms.Kalpana Arvind, respected another department, Dr. Jayalakshmi, Dr. Sudhaman, Dr. Kumaresan, distinguished faculty, dear students. I am very happy today that the outstanding scientist of ISRO is here to share her experience and exchange the ideas with you. On behalf of NGR University, I extend a very warm welcome to our distinguished scientist. Welcome. In the month of April, we conducted national seminar on space technology. Madam delivered an excellent lecture on the topic of sensors. Madam has worked for nearly 3 decades in ISRO and especially in the field of sensors. She worked in Chandrayaan 1, Chandrayaan 2 and Chandrayaan 3. All communications and sensors she designed and developed. So we are so fortunate to have her here Thank you, ma'am, for giving your acceptance and presenting your lecture here. Practical experience. She has shared her experience and knowledge to our students. Dear students, you all know that now we are celebrating National Space Day on August 23rd of every year. August 23rd, 2023, Chandrayaan landed on Moon. That day is remembrance of National Space Day. This week also we are going to celebrate it. That is tomorrow. So this is also a part of National Space Day celebrations. This lecture. ISRO is now one among the top 4 countries who landed on Moon with our Chandrayaan, especially in South. ISRO, Government of India has allotted 1 lakh crore for the development of ISRO activities. In the year 2035, ISRO is planning to establish the Indian Space Station. In the year 2040, the project vision is Indian astronauts will land on Moon. So, the tremendous expansions are going on. Our space economy is marching towards 3 trillion, another 5 years time. Many of you can think of taking your career in ISRO and space activities. We have, as of today, 450 startups already have come in the past 3 years in the space field. And if you want to join in ISRO, you have to appear for GATE examination. If you are qualified to GATE exam, easy to enter into the ISRO. We have already given you a lot of course material while you are doing first year itself. So I request all the students to concentrate preparing for the GATE exam. It is going to be held in February 2026. So with these few words, once again I welcome Madam for this technology talk on the sensors. The topic says given satellite sensors and its applications. Those who are interested to know about our the engineering satellite activities, in this building, 5th floor, we have the Space Technology Center. Our students have developed the CubeSat satellite. The CubeSat application is, the payload is to help our Indian fishermen. Every day you find in the newspaper, Indian fishermen are arrested by Sri Lanka. Navy or Army. In order to avoid that, our satellite will help the fishermen to identify the international border of fishing. That is the concept which we have developed. And that will be demonstrated tomorrow. And if you want to visit the CubeSat satellite developed by our students, CANSAT developed by our students, and a rocket developed by our students, you can visit the Space Center in this block, 5th floor. Also tomorrow afternoon, 2 o'clock, we are planning to demonstrate in the UOC block grounds. The satellite with the drone. Drone will take the satellite to 500 meters. From there, the data will be received by us in the ground station. So with all these things, we appreciate your interest in learning more about the satellite activities in the rocket. Our chaplain is very passionate about it. The satellite developed by our students will be launched by ISRO coming month of November. We are one among the 75 satellites, the Prime Minister's vision announced by our Prime Minister in the year 2021 in New York, United Nations General Assembly. So MJ University is the one university who got opportunity to develop the satellite in the Prime Minister's vision. These few words again, I welcome all of you for this talk. Thank you.
Thank you so much, sir, for motivating our students. You are a great asset to our university. Thank you, sir. பெண் ஒருத்தி திறமையால் உயர்ந்தால் சமுதாயமே முன்னேறும். பெண் திறமையால் விளங்கும் போது அவளின் வலிமை உலகம் வியக்கும். When a woman rises with her talent, the society progresses. When a woman shines with talent, the world marvels at her strength, which goes really true to Ms.Kalpana Arvind. I now request Dr. Kumaresan, Professor, Department of ECE, to introduce the guest for the day.
Good afternoon, everyone. I would like to introduce our chief guest, Ms.Kalpana Arvind, ma'am, outstanding scientist, associate director, retired from the Laboratory for Electro-OPTICS Systems, Bangalore. Graduated from the PSC College of Technology, Coimbatore. She later joined in the sensor divisions of ISRO Satellite Center, currently called as UR Rao Satellite Center, as scientist in the year of June 1986. After her engineering, she was assigned to the work of developing sensor processing electronic packages for the Indian National Satellite inside 2 series. Till date, more than 40 packages were flown, including Chandrayaan-1, Chandrayaan-2, and Chandrayaan-3 Mars missions. She has also designed and developed advanced fiber optics based gyroscopes and MEMS-based sensors for inertial reference unit and accelerometers respectively. Under her guidance, laser and vision-based navigational sensors, rover cameras, and payloads were developed. She has been leading top responsible positions in ISRO for past 38 years. She is an active member of various review committees. She also has more than 55 publications on the various works done by her at ISRO. She has 2 patents and also applied 1 more patent. She has also received several awards like Women Scientist of the Year 2005 by Astronautical Science Society of India, received from former President late Sri APJ Abdul Kalam. Received 1 more award received from Team Awards from 2017 for developing the dual-axis fiber optics gyroscopes flown in GSAT-19 under the leadership from Dr. Sivan as chairman. She has received many such as awards which are feathered to her cap. We were really proud to have you with us and to learn more from you, ma'am. Thank you.
I kindly request Ms. Kalpana to share her knowledge with the students.
Good afternoon to one and all for sitting here. Let me thank the Dr. India College Management, and HOD Electronics and Communication Engineering here. And I'm back in this stage at the second time. Thank you for inviting me. And today my voice is little bit down. I was had fever and due to travel from Karnataka. So kindly bear with my cough and things. But still, let the lecture go. This satellite, people, are you familiar? What is this? Name? Name of the satellite? NASA, ISRO. You see the top right? NASA, ISRO collaboration. This satellite, we started the work 10 years ago and successfully they have deployed the top 12-meter antenna. So that work was done, and this work with the collaboration, so much effort has gone in this. So upcoming time, people who are working in the science related data, where they are going to use this data, it is going to be one of the user friendly, and they are going to use it for the and for this also satellites, every satellite sensors are required, but this particular satellite is something special. So that anyway, just I wanted to put a word to you people. It is going to do the imaging of the Earth in synthetic aperture radar in L and S band, and it is going to cover the globe in 12 days. So the same place it can cover again 12 days, once in 12 days. That is the past. It's going to give accurate results. So all our remote sensing what we have done, it is going to give 1 order better, 2 orders better. So it will take another 2-3 months till everything makes. They have to characterize, switch on every channel, test, then only they will give. So that will take some more time, but the best, the antenna deployment is over. So coming to my talk today, I'll talk about the basics and then attitude sensors, what we are doing, and rate sensor, which is called the gyro, and MEMS-based systems also have worked. So I am not able to cover today navigation sensors already. Time is running out. So today, just what is spacecraft motion? Once the spacecraft is taken by the rocket and it gives a push, with that initial push, what it has get, with that push and the gravity of the Earth, it goes around. So if you are using a polar orbit, according to the polar orbit or the communication satellite. So the translation motion and the rotational motion, both are required all the time. So for all these activities, the center of the mass from A to B, the position and velocity also be used from A to B. Anyway, satellite initial velocity is given by the rocket. With that velocity, it will continue to go. With respect to the Earth position, where it is, we need to always find the position. Then all these things are done automatically and using space navigation. There is a mission team who works on this. My topic is how we are going to measure the rotational motion. That is, when the spacecraft is rotating, changing its orientation, that means direction, we are going to measure it. That is the angle, and at what rate it is changing. That is the attitude rate. We are going to use sensors to measure it. So how we are going to define is, if you see first, there is a glass. Whether it is up or down, you can say down if you are looking from this side or from that side. But if I put a table, okay, it is sitting on the table. Is it sufficient? No. You need one more reference. Okay, now it is in a house, sitting on top. So all these things, if it is available, then only the attitude is represented. So this representation of attitude is given by the sensors. So before going further, like our, either if it is a ship or a flight, or a normal aircraft, or a rocket, or a satellite, the axis definition, whatever I am giving, it is common to all of us. The spacecraft movement axis is called roll, and the axis which is pointing towards Earth is called the yaw, and perpendicular to these two is called pitch. This is common for whether it is a remote sensing or a communication or an interplanetary mission. So always we define our sensor outputs with respect to yaw, roll, pitch of the spacecraft. So I just wanted to talk about sensors. What is the difference between a sensor and a transducer? So what physical parameter, if there is a sensor is sensing, and then I have to convert it into usable or readable data. So that is the sensor. Transducer, what it does is one form of energy into another form it does. So when my environment can be a light or a heat or a vibration or any flow of liquids or something. So that is what I am going to sense, convert it into electrical signals. Normally, this change in sense can be a resistive, capacitive, which all of you know. The six principle, it will be there always. So this is the thing what I am just representing here. The same thing applies to all our things also. So normally the processing wise anyway, you have to sense these physical quantities, then convert that thing into electrical quantity. The output, whatever is there, it should be readable. That means you need to do further amplification, or you have to digitize it, or you can make it into directly analog voltage itself. If you want, you can transmit. But in a world where analog world you can use, and you can use it in closed loop. But when you want to read it on ground, you have to digitize it. So then signal processing also comes into picture. And when you have one or two, it's fine. But when you have number of temperature sensors, what is required per spacecraft, what I have used in my first design was almost 256 thermistors and 40 PRTs. That much order will be there throughout the spacecraft. So then you need to do the data acquisition. So all those data have to be combined into a single stream and then send it to, that means you have to multiplex all the signals and then convert it into ADC. Then we give it to telemetry system, which will transmit to ground to know the overall health of the spacecraft, or you can send it to a heater enabler like a thermal control system, who will either heat or cool depending on a payload, what temperature it has to be maintained. Accordingly, they will either switch on the heater or a cooler. Then that is the application by connecting to the what is the way it is readable. So finally, what we are doing, the physical change, what I am measuring, I am converting into usable data. So if we see the characteristics, all these sensitivity, linearity, hysteresis, temperature dependence, frequency response, noise, drift with respect to time, and saturation of the signal, cross-axis sensitivity. Because when I am putting a sensor, I cannot put one sensor alone. I need all the three directions. So if an accelerometer is there on all three axes, whether one axis acceleration is it sensed by the other axis. So that cross-axis sensitivity also is really required to be done. Other specialties, dynamic range normally, and what accuracy we are going to measure. Whether it can measure the smallest resolution possible. Some cases, operating temperature ranges are really important for us, and power supply. In ISRO, most of the things when I started working, all were operated at plus minus 15 volts. Now things have come to 3.3 volt, now 1.5. Further future it is going to come to 0 to 0.5 also. The technology what those days we worked is centimeter to now nanometer is the growth in electronics. So things will become different, and anyway, which I will be talking about that. And output type anyway, analog or digital or mixed. Then physical dimension and weight of the sensor, what I am selecting also is very, very important. And construction of the material, because in space what we can use on grounds directly I cannot use. The radiation environment and the temperature extremes, it has to be survive and it has to work depending upon the mission length. In ISRO, I think if people know, I don't want to continue further the talk on this, because these are the four main areas where ISRO is making the satellites. And for all these satellites, our main type is Indian remote sensing satellite or the communication satellite, which is called INSAT. Now they are calling it as communication series like that. So the pointing accuracy, that means once the satellite is left in the orbit, all three axis angle should be within that. That means the 3 sigma value is plus or minus 0.05 degree. So that is the order it has to maintain, means the sensor which senses the input angle should be one order better than that or two orders better than that. Because what I am sensing, control system has to read and correct it using the actuators. So the actuator errors and control system errors also has to be taken into account. So always our sensors, we normally make it more than 2 order better than what is required. So for communication, the antenna only is going to point, so accuracy requirements are less. Again, whether you go to Mars or geomission or lunar, the spacecraft has to fire the engine and go to the different orbit. Each and every time, whenever we fire, the delta V, the velocity what I am giving to the spacecraft to move away from the Earth's gravity, has to be measured by the accelerometers. And the orientation, whether what direction I am rotating and moving and firing, is sensed by the sensors. So both attitude sensors and accelerometers are required in all these operations. So finally, how sensors are used is, they are like human, how eyes are important. Sensors are eyes to the satellite. So how we use the sources, we make sensors as absolute sensors. That means the error what I measure is, there is no ambiguity in that measurement. So we call always our sensors absolute sensors. So the source what is available in space, sun, star, Earth's infrared radiation and the magnetic field, we use as the source and we make the sensors. So different types based on the source what I am using, we call it as Earth sensor, sun sensor, magnetometers. And the other two sensors, fiber optics and MEMS sensor, comes for the rate measurement. So that I will come to that later, because any sensor, when I am rotating the spacecraft, the angle changes. So before rotating, normally gyros only will be there in the control loop. The gyro will drift with respect to time. That is corrected by the absolute sensor all the time. So that is happening in all the satellites, in all the missions, during all the firing. So it will give the correct update at the start of the fire, and gyros only will be used in loop to final till the 20 minutes or 30 minutes firing. Gyros will be there. So why we are using so many sensors? Why one sensor which is very high accuracy, will it not be sufficient? Why I have to use? Because different orientation of the spacecraft, whether it is a polar orbit or communication, sun also goes away, eclipse comes. So that time star sensor can be there all the time, but star itself, if something happens, it can also lose track of the stars. Once stars are not available, spacecraft has to be kept in safe mode. So always, one way or other, 2 or 3 different versions of sensors are always required, which I have just compared in this one single slide. So how we are using the sensors in the feedback loop? If you see here, what is the reference or the desired direction? That is the way attitude control electronics person will do. Using the actuators, he is moving the satellites. The dynamics is changing, so the rotation angle theta and the rate of theta, that is theta dot, both are changing. So the rotation angle is measured by the attitude sensors and the rate is measured by the gyro. By integrating both, again we are correcting the errors. So this will be happening continuously. So that is how we will reach the correct target. So main brain behind any system is attitude and orbit control system. It takes the input from the sensors. Output is either the thrusters or the wheels or the magnetic torques, they are the thrusters, which will correct it in loop. So the control system is connected with all the subsystems like power, telecommand, telemetry, payload, everybody is connected. Coming to sensors, what are all the different inputs we need to give in the sensor systems? So first, what are the different types? Suppose if we take ELECTRO or the latest your SPADX mission itself, whether you need attitude sensor, what accuracy, what is the field of view requirement. If star sensors are there, I will show you the design. The mounting constraints are so much because star sensor cannot see any bright objects, any reflected light should not be seen by the star sensors. And what will be the update rate I can give? That is the reft pulse or the sync, because always it is any operation is done in synchronization with the control system. clock signal. And on-off command, any data commands are required, and thermal control, because not all sensors can work at minus 150 to 200. None of the electronics also will not work. And some of the detector will limit the overall performance of the spacecraft. So normally we limit the operating temperature of a highly accurate system like star sensor under 0 to 40, earth sensor minus 10 to 50, and sun sensors, solar panel sun sensor alone can go to minus 180 to plus 180 also, it can work. But other things we normally limit it to minus 40 to plus 60 and all. So some levels of that, and shock and vibration levels, because every operation in the rocket and the ejection and later on any firing happens, all those things gives us small shocks and vibration. So all these parameters also are important. And then what is the output? Who is going to take my output and what type of interface? Previously, now everybody knows serial interface, how much it is in your CubeSat also, all interfaces are serial interface. It has made your life very easy. The number of lines running from one system to the other is very simple. Earlier, when I used my first sensor, it was full, the integration was full of harness, wires only. Now if I see, if you use the MIL 1553 interface, the speed is faster compared to your I2C or serial interface, because our data transmission is faster. So we are using MIL serial interface and it is EMI free. That is one more the advantage. And normally, whenever I am giving a output signal, whether it is valid or not valid, is given by one hardware status bit, like sun presence signal or a data presence signal or a data validation signal we give. So the control system will, by seeing that, they will blindly use our sensor data. And the polarity also very important. When I am telling positive angle, positive, that means they have to rotate negative to correct the error. So that polarity wise also we normally test, and the sensors, whatever polarity we are giving, they will be tested in hardware in loop simulation test with the control system, with their logic, and our sensors are validated on ground itself. So none of the time the polarity mismatch will never come. But while mounting, if you make a mistake, again polarity difference can happen. So nowadays we are planning to give output in 32-bit also. Olden days only 8-bit. So this is how the electronics, how we have evolved is, actually my time, that time only just integrated circuits have started, TTL and CMOS ICs have come in the 80s. And before that, tubes and balls were there, radios were having only that. But I have not used the tubes and balls, but just heard about it. But we have used integrated circuits only. Those days TTL was the main thing. Now everything is gone into a ASIC, it's application specific ICs or a field programmable gate arrays if it is a full digital logic. So that is how the technology has grown from discrete devices to ASIC. And packaging wise also. Normally those days only plated through holes only were there. Now SMD, surface mount devices, if it is analog, HMC, hybrid microcircuit versions, and earlier under 2-layer board only, now multi-layer board. Not only that, flexi-rigid PCBs, which we can flex the PCB and bend, and overall we can reduce the overall dimensions. And motherboard, daughter board type, now it is full electronics package, from a package to a single card, a tray type. Now that itself, now people are going to 3D. Now last will be system on a chip. This is the future technology. Still we are yet to reach 3D packaging. We are trying now. That will take some more time. So these are all the different quality levels. What we use components in ISRO is not the commercial components we use here. Problem is the radiation environment is very high and sensors are always mounted outside the space. So it has to withstand the radiation environment. So we use highly qualified components. If the component is not available to that level, we make it by way of screening. So for upscreening also we have a lot of procedures. So follow that, and once it is clear all, then use that items. So these are all some of the things. And what standards, for everything we have a standard, and with that process qualification only we can go further. So if we start a sensor design, starting system requirement means mission objective, what they wanted. From there we start configuration, piece by simulation and testing that everybody will do, and then procurement of action for the detectors. Parallelly you do the schematic and design reviews in the design phase. That is for the ACDRC. It is required for because sensors means optics is required, electronics is there, mechanical is there. So all the three reviews will be there. Then we need to give parallelly input to the thermal system. Then do the development. Parallelly software development, FPGA if it is there. Then fabrication of PCB also will be going. Then one temporary assembly also we do with all optics, PCB, card wiring, card testing, mechanical parts, everything will put together, we will do the test. Functional test and environmental test, this is called the design verification phase. Then once design is verified, once again review of all, whatever you have done, everything has to be cleared by the review committee. After clearing, then it will go to the permanent assembly, testing and evaluation. That is the design validation phase. After clearing, but the design validation phase will be cleared once engineering model, which is stressed to 10% of the flight level. That is the time only it will be accepted to spacecraft. So I have to prove a margin of more than 10% in the design itself. Not only that, the system should withstand EMI/EMC because all communication satellites, the bandwidth and frequencies are very, very high, and antennas also are kept outside. So interaction with the system will be there. So how to protect myself with the EMI/EMC, that also we have to take care. And software development also, it is not a simple task because hardware by testing and different temperature environment will come out, but software testing, even if you do 100 times, the software bugs will never come. It is a full closing circle, all the time analyze, implement, experiment, design. It's a cycle, never, if it works, fine. Next time when you do a change, again the same cycle, but every time we do the test and all this time. And every design quality assurance is very, very important. Without quality people clearance to never fly. And if you are buying any component, the upstream component, why your prices are very high, all the components which is produced in the factory is fully tested. So the initial mortality rate is removed, and where the normal life or the useful life, the flat curve, it's always called the bathtub curve. That is the time where we will be using. So we will ensure that 5 years mission, 15 years mission, what type of component, what type of radiation levels, that way only we will select, and that design will be cleared by QAT, because if the component can work up to 200 watts, I will never operate it in 200 watts. We normally, olden days, we were operating 25% of that. Now we have, based on the knowledge and experience, we are able to operate 50% of the design. Some cases, if the life is very short, we are going up to 75% of the life. So that if you operate and keep a safe margin from the design of the any component or the detector or the sensor, its life is better. If you operate to the full maximum, it doesn't work long. It is applicable to all the design also. So if you take a sun sensor, that is a system sensor level overall. Again, individual sensor wise also, different inputs are required and outputs will be almost most of the time same only. So whether, because sun sensor also we have different varieties. So whether you are going to do one solar constant, because whatever I make, I have to test it on ground. So we have simulators which can simulate 0.02 solar constant or 1 solar constant. So 0.02 means I will put a neutral density filter before flying, so that the calibration will match once I fly it. So some sensors like solar panel sensors, it will be seeing the sun all the time. So it will be tested with the 1 solar constant simulator only. See the same spectrum, we see the visible spectrum only we are using. The silicon photodetector is the solar cell, and charge coupled devices, They are also in the visible band they are using. And infrared only, we are not getting microwaves, all these detectors we are not using right now. We don't have the necessity. So this is the spectrum. So this is how the visible band, what is there, the nearest spectrum, what is possible is simulated in our lab. So this is in-house. Earlier we used to import the solar cells. Now LEOs, we have the detector group where they themselves are fabricating the solar cells, and the solar cells right now, we have from the past more than 25 years, we are using our own solar cells by reducing the import options of solar cell import. And not only us, we normally give it to students also, and some people have replaced and some people have bought the solar cells also. And this is normal solar cell. When the fill factor is better, it will be the efficiency is better. So simply, so these are all the different varieties of analog cell sensors what we have flown till date, and these analog sensors are being used in Mars, Chandrayaan, and all communication satellites. They are being used. The principle is very simple. That is coming in the next version. Why it is called analog is output is analog, because current whatever light is detecting, output is voltage. We are making current to voltage converter amplifiers only. It's a very simple design. Next slide it will be there. So current voltage converter, use a summing amplifier to generate the sun presence signal. Use the divider option to generate the angle output. Why the divider option means any cell output cos theta effect will be there. So the division if I do, cos theta effect will become cancelled, so it will become a linear data. So this is how the data will be. We used a simple triangle pattern, top side one slit, in between the air gap is the mask. So this is how sunlight enters and how two solar cells are used. Cell A output, cell B output. Do the A minus B by A plus B, you get the AOC output. So the linear range and the saturation range all are shown here, and the sun presence range also is shown here. So this is one direction, we call it as measurement axis. The cross axis also, the sensor will be the output. So both measurement range and cross axis range also are available. And this is how the field of view, I told you, measurement range and cross field of view range. That's a small sensor, but it gives output to this much with 0.5 degrees the accuracy, and plus or minus 45 degree measurement, and plus or minus 62.5 degree. So we have put 4 sensors. So throughout the spacecraft it covers, and 24/7 we can get where the sun is there in the spacecraft. If you see solar panel sensor, same principle only, here also it works, but its field of view is limited because cross field of view it will see the panel itself. So we are limiting it by a small hood like thing. That metal strip you can see both the sides, which will limit the field of view in the other axis. And this is how it is mounted. Normally it will have 2, 1 for the redundancy. And this is same principle what I have explained. Actually the output is given to the solar array rotating person, so that where it is null it will generate the maximum power. So operating automatically does. So the solar array drive assembly team takes the output and directly controls. Our control system will take and give it to solar array drive assembly to correct it in closed loop. And the other simple sensor is called the 4-pi iridium sensor. Previously it was mounted on a PCB separately. Now using the flexi PCBs what I have seen, everything can be folded and made it into a small things. There is no wiring involved, including the connector. All are through PCB. There is no wire here. That is the technology now. So this is the way it is flying. Now for the nano satellite, we made it into a single sensor with a single PCB, which can be pasted in any of the panels of this, our Indian national, actually INS 1C, 1D, we have flown like this. So it can give 4 pi stereo by putting 4 sensors, full 360 degree we can cover. But one disadvantage is because it is fully exposed, any reflection comes also, it gives us a signal. So it is always used as a safe mode sensor only, not as a control sensor. As gas, we can use it in the closed loop. So this is how it is mounted in the spacecraft. And yaw sensor, yaw output, roll sensor, roll output, pitch sensor. If it is orientation different, so yaw can give the roll can give other axis. It's depending on the mounting. Where we are showing that 51, 52, 53, 54. That is the sensor size with respect to the spacecraft. So any appendage, anything, even including the earth, when light falls on the image, that also it can give a signal. So this just mounting alone we are showing here. So normally the 4 pi sensor, which is cell itself, is exposed outside, whereas gas it is going through a glass plate. So not much degradation. But Aditya L1, what we have seen was the number of times in that environment it went through so much. So 40% degradation happened within the first 10 days of the launch. It has 26 times it has crossed the radiation belt. To avoid this, our detector team has come out with a silicon carbide detector where it will not get degraded by the UV light. So it operates in the UV light. So this has also flown in INS 2D mission. So the performance was normal here. Coming to digital sensors, again here also we have varieties of digital sensors from olden INSAT version, this was Rohini satellite, to now Aditya L1, high accuracy sun sensor which is giving roll and pitch control to the spacecraft. This is arc second accuracy. I will show you the comparison how we have grown from a degree, pi degree sensor accuracy to arc second accuracy using a sun sensor. So this is the table if you see. Only thing is the dynamic range, what is given in the highest sensor, dynamic range is limited, but the null accuracy is almost arc second. And the performance what we have committed to mission was 4 arc second, but on board we have seen 1 arc second is the accuracy. See the first version of digital sun sensor, how it is called digital is we made a gray coded pattern on the pattern itself was made in the block. Top slit, bottom a gray coded pattern, then solar sensor pasted to that. So the output whatever comes is digital. That's why it's a digital sun sensor. So the current and each sensor 12 cells were there. Current to voltage conversion, and then they are cosine curve. Any things will be like a cosine curve. From the cosine, you have to make it into linear, convert it into digital with a threshold. So the lot of electronics, everything was there here. Then later on, the technology going to use like this. People come out with CCD, charge coupled device. Use a payload. From the payload, use the CMOS detector. So made it into active pixel sun sensor. So from solar cell to we have gone to charge coupled device version. So this also we have flown in many missions. Later on we used the same thing using a N slit. Instead of single slit we used an N staped slit. And with that we were able to reduce the size and weight because in space, the number of weight, even if you reduce 10 grams, 20 grams, also people were really very happy because from 1.2 kg, the sensor head, we have reduced it to almost less than 100 I think 75 to 100 grams, that weight-wise 25 times we were reduced. So that is how the sensors were head-wise upgraded, but number of heads processing also we have improved. So it can be used like as how so many sensors were there. This particular sensor we have flown in NISR because they need in different locations when it is rotating. They want the field of view coverage also more, because this sensor almost 60 plus minus 60 degrees the cross field of view as well as measurement field of view. And technology also come with the FPGA, so everything was included there, and 2-axis information we can get using this. So this is how the end state slit when the light enters 3 dots. As the sun moves, where it moves in the linear CCD array, from that using the calculation we can tell the angle. But here the intensities will be reduced using the neutral density filter. Otherwise, charge coupled devices will bloom. And HAPS is same thing, only instead of single pinhole, we use the 4 pinhole, and the dynamic range is reduced so that we get better accuracy. So its noise was almost less than 1.1 second. That is what we got the data also. And the 2 sensors were mounted, and it is continuously giving the spacecraft roll and pitch measurement. So 4 pinholes we have used. And because once I tell I am measuring 4 arc second, people will ask us, how did you demonstrate it on ground? So we made a special setup, same sun simulator, the rotation stage and the chamber to maintain the temperature, and rotation stages where 1 arc second is the accuracy and resolution of 0.03 arc second, so that when I move 0.03 arc second, whether it's really measuring or not measuring, so that way we maintain the stability of the sensor and demonstrated the performance. And whatever we did on orbit, the performance was far better than what we got on the ground. So people are really happy, and it is being used continuously in Aditya L1. And this is how the sun simulator facility, our xenon arc spectrum will match the 1 solar constant spectrum. So that is the setup here. And all these sun sensors, electronics wise, we were doing in the processing electronics, not only sun sensors, even temperature sensors, pressure sensors, all were done in one particular package previously. Then later on, to reduce the size and ease of compiling the data, so thermocouples, thermistors, all those processings were shifted to the telemetry, because finally the output was going to telemetry only. Who is controlling the full data? So we told them and made all these things, we made it into a single SIP package, single inline package. So that is what they have used. This blue colored ones were that type of resistor network like this. So packages which were weight of discrete version to HMC version. Later on, the HMC packages also is made into a single card tray type. The tray type only is right now being used, and those trays also, because finally the user is the control system. So directly we have given to control system people, now they themselves are wiring, testing and using it. So this is how the cellular processing inside, how each and every versions are connected. So for Indian remote sensing satellite, magnetometer also will be there, 4πSS, SPSS, and for remote sensing satellite, couple fine temperature sensors will be there. But for a communication satellite, only thermistors, PRTs, SPSS, 4π earlier we have used, now we are using only CAS. So apart from that, all other things were made it into simple. And if you see the logic wise, everything we have made it into a HMC version, so that the package size is motherboard, daughter board has become. Anyway, that's how the single inline package I was telling you for thermistor processing. This is the last point. So So everything was made it into a smaller version, and how each and everything has to work, because when one system fails, half the system will be connected to redundant. So half main, half redundant. So the powering wise, how the multiplexing wise, even if one bus fails, still I need to get all temperature data. So that is how the power supply itself was selected, switched or diode ORed. So all those combinations were done, and that is final. This took some time, but now it is working very beautifully. No single point failures is taken care here. So this is how we made, how the powering scheme has to make it so that none of the system, even if one bus fails, still I should get all the output. So this is anyway magnetometers, because it has flown in Arvind 2 till the latest Aditya L1, and we have a high accuracy magnetometer payload also has gone in Aditya L1. And mini-mag type of analog magnetometers we have given to ADA ADE also is there, also using our sensors. And for nano satellite bus, again analog magnetometers are very required, that is the nanosat magnetometer. Because nanosat only sun sensor and magnetometer is the backup, star sensor is the main sensor. So because again there we need to get all three attitudes. So when sun sensor will give two axis only, using magnetometer only we can get the third axis. So nanosatellite bus magnetometer is also very important. So the highest accuracy payload we can go from 500 nanotesla accuracy to a 1 nanotesla accuracy, and that was already measured in Aditya L1 also. Now coming to F sensor, we have so many versions. Finally, now we have only the last 2-point FPGA F sensor version and mini conical series 1553. These two versions only, remaining all versions are outdated, and even this version also, once star sensor gets stabilized, we are making a thermopile based safe mode F sensor, which will not use this type of complex motor technology. Simple technology people are already developing, so that will be used as a safe mode sensor. Now this is like a backup sensor. Right now we are using it in place of star sensor. For geo, when it is looking at the Earth, it is the circular disk. Earth is like 17-degree disk. So what we are doing, the infrared radiation emitted by Earth is hot, whereas space is very cold. So the change in temperature is measured by a bolometer, nothing but the resistance change. Heat change is changed by resistance change, that is biased and got output of electrical output. So that is simple principle, but to get the roll and pitch measurement, because two-axis measurement, we need to do a scanning system. So we have a scan mechanism which moves from east to west. To get the error better, we have two scans, north scan and south scan. When you average both, you get better accuracy. So 0.05 degree pitch and roll 0.08 degrees is the range what we were getting, and its weight from 1.7 kg 5 watt power. We have reduced it using ASIC and FPGA based design. First, the initial design was with the TTL-IC based design. And this allows the too much complex design in the Earth sensor, because the scan mechanism is different. Automatically it has to start, once the system is on, it has to switch on automatically. For that, the encoder, sense coil, mirror, there is a mirror to collect the scan things to pass it on to the detector. So north detector, south detector, which zone amplifiers, then processing. From the processing again generate polar pitch, at the detection signal, then the final output to LOC. So this much complicated both in mechanical alignment and each and everything. That's where we wanted to come out of this. Whereas star sensor, though it is costly, processing is simple because computer is doing most of the things. So how the Earth is scanned and how we are generating each and every signal, how the errors are calculated is shown in this. Whereas if you see in remote sensing, where polar orbit, the height is less we cannot do that type of linear scan. We need to do, because we will be seeing some part of the earth like what is seen here. So we use two scanners, two earth sensors, one on east and one on west, so that whatever it scans, here it has to rotate 360 degree. So we have used a motor, it's a brushless DC motor. So again here lubrication is the big issue. So the temperature should not go below. So whenever it touches, we have a heater built near to the motor, so that the lubrication process will not get stuck. Otherwise the motor will stop. If motor stops, none of the things will work. So this is the things what is worked, and now these sensors are working as a backup sensors only. Star sensor is the main sensor. So coming to star, how all those sun sensor or earth sensor, it gives two axis information only. Third axis information has to be taken from the sun sensor or the magnetometers. Whereas star sensor can give all three axes with accurately, because the constellation what we see in the star pattern, whether you are looking from Mars or Moon or on Earth, it doesn't change. So the design doesn't change. So we use the same design. So it gives very accurate measurement, and the constellations are mapped very well with the time. So it is present in all, and it is a point source. The accuracy is very, very high. So how we are doing is, it's again just a camera, how it captures us. It captures the stars pattern. Compares the stars pattern, I will come back to that. Star catalog on board, and then it finds the matching the pattern and estimate the altitude. So it is useful whether it is LEO, GEO, interplanetary, all same design. So here there are a lot of requirements are there. Normally for star sensor anyway it can give update rate as 10 Hz or 8 Hz. And when we are doing imaging operations, when we are taking the imaging, normally gyroscope only will be in loop, star sensor will give the update. And because gyros drifts are there, so drifts will be corrected by the star sensor update. And spacecraft position is given from the laser ranging, which is done from the control center. And time references, onboard timer also is there, because when you are doing imaging, which point where you are imaging, unless you know precisely, you cannot tell which point you are pointing. So all these informations are accurately available. That is how your Sindoor operation we were able to do perfectly using star sensor and the gyros, which was flown in cartography, which gave accuracy one order better what is required. So the precise place, how defense people are using our information only. Carto 3 satellite. So the reference wise, how we are doing is either inertial reference or earth centered, earth fixed. Because when I am telling with respect to what axis reference I am giving, that is what is depicted here. And how we do in the star sensor wise, first initial orbit when the satellite is ejected by the rocket, it will be in tumbling mode. Then slowly the tumbling stops and then will come to the safe mode. Then sometimes if you want to keep it idle mode, means because still it is tracking, unless it gets to the correct point or whatever points required, then it will go to the inertial pointing mode. Once particular star pattern is captured and it is next point where it is moving based on the rate at which spacecraft it will put the place. So from the track mode to it will from lost in space mode it will come to the track mode. Sometimes if you want to rotate the spacecraft, look at some particular angle or particular point, you have seen somewhere, but if you want to rotate to another means pointing towards Earth. So that type of mode is possible, or some particular target in mind if you want to do is also possible. So all these operations when you want to do, you have to rotate the spacecraft in the specific directions. So that orientation and knowledge is what we are calling it as the altitude determination. So if you see in geo orbit and LEO orbit imaging, if you want to do, the first one is the communication satellite, the other one is the LEO orbit. So the strip wise how it is, each time short visibilities, with that short visibility times how we are going to do. So multi-spot imaging, and when you want to do so many points coverage, how two satellites they are using it, and the satellite how the very fast it can move, agility wise, all those things. LEO requirements are very high. Even GEO is there, but LEO requirement is more. So how star sensor work is, the star pattern is captured by the detector and it is focused. Actually, there is a big optics is sitting in front. After the optics, there is a big baffle. So this big one, what you are seeing front end is the baffle, so that no other stray light enters the detector, and the behind the baffle only is the optics. Then optics center point only is the our CCD detector. Then the detector output bottom point is the electronics with the microprocessor based design. So you will compute the centroid. Earlier we were having different types of CCDs where image zone, memory zone, then readout things were there. Now active pixel, everything is coming out as digital. So simply if you clock it, directly output comes, and digital output comes. So first time it will look at the stars, autonomous pointing mode, then inertial altitude, whether it's available. Once it is available means it will go to track. If it is not there, again it will try to get the star pattern, it should match with star catalog. Once it is matched, then it will come to the correct attitude, it will give it to AOCS. So this attitude, whether I can connect 3 or 4 bits, now we are planning Gaganyaan mission, they want 4-level redundancy. So number of electronics we wanted to reduce. Heads alone we have put 4 electronics, common processing and attitude processing unit, main and redundant. Any head can be connected. Still AOC can get information continuously because Gaganyaan mission, human are involved, they don't want to risk anything. Normal satellites, only 2 types or 3 types star sensor only are sent. Now in Gaganyaan, 4th level redundancy they are asking. So this is the how roadmap of star sensor. If you see accuracy wise, Mark 4, which is Carto 3 and Carto 3A, the accuracies are 1 arc second. That is the highest accuracy star sensor which is proved. So to meet this highest accuracy, what are all the problems we face? First thing is star catalog, whether it's correctness and each angular sensitivity of the sensor, SNR calculations, error modeling and correcting, on board what are all the external factors. And I was telling you, when I mount the star sensor, when the panel is deployed, it should not block the field of view of the star, and sun should not fall on the sensor directly. So the mounting constraints is a big mistake, big problem for us. It's not a mistake, big problem. So even if I want to put third star sensor, there is no place in the spacecraft. With great difficulty only people are putting. Accordingly, either the panel size has to be reduced or the sensor or place in one panel, they are putting all the 3. There is no other appendages or anything. So that is one big issue for a star sensor. And not only that, earth spin and earth revolving, all these elliptical things and thermal effect, gravity effect, all these things affects our sensor. And because the change, whatever I have aligned in our lab, it changes on board also sometimes. So small changes, corrections, then we on board also we do calibration. Sometimes the vibration, because some wheels are continuously running for the actuators. So that vibrations, continuous vibration start sensor has to work. Sometimes the mechanically though it is isolated far away place, sometimes 1 arc second accuracy if it has to work, it has to be mounted on the optical bench. So that is how we solve the problem. So this is the optics. If you see the number of lens what star sensor is using, that star optics should not move when I want to measure arc second accuracy. So thermal distortion of any mechanical sites or the mounting blade where I have mounted also should not change. Alignment change, anything will affect my final accuracy. Coming to gyroscope where I have worked, normally people use mechanical gyroscope. Even today, some of the rockets we are using still mechanical gyroscope. To now also some of the satellites, even micro satellites, we are using mechanical gyroscope. Optical wise, solid state technology. That is the main advantage, and main issue is here nothing is available in this level. All fiber optic components are available in commercial grade. So use that and make it work. That was the challenge here, and the principle wise it works on the Sagnat principle, where what we are doing is when you send the light in a fiber coil, the coil can be 1 kilometer or a 3 kilometer, because the formula wise the change in rotation rate or the change in phase is directly proportional to the length and the diameter of the bobbin what we are seeing here. So the light when it enters in clockwise and counterclockwise, they will come in the same phase when there is no rotation. When there is a change in rotation, they come at a different phase. So by measuring the phase difference, I am measuring the rate. That is the principle. Telling is easy, but 10 to the power minus 5 or 10 to the power minus 6 rate measurement is the capability we were doing with the commercial components, and it was a challenging task for us, but finally we succeeded it. So this is the order. If you see the sensor, if you keep it on for 1 hour, the drift will be 0.002. That is the sensor what we have sent in Carto 3, and along with this gyro and 1 arc second star sensor was made that single operation possible. So these are all the different components which we have upscreened and used it. And technology, everything was made in-house. And coming to MEMS, under 5 minutes only, because anyway my throat is also going in there. Because too much things absorbing in one day also is too difficult. Anyway, MEMS, people might have heard about it. We have a fab, but right now the fab has become deep reactive ion etching fab we have, and we made it using a capacity based foam type structures, and this particular MEMS sensor was used in Chandrayaan 2 and Chandrayaan 3 also, to measure both inclination of the rover and even lander also, and to measure the seismicity of the lunar surface, because we made a high accuracy version using a different MEMS chip. So both are worked very beautifully. I will show some of the signals. So this is how that almost 10 nanoG level vibration we were able to capture in the, when moon surface, if something rover movement was captured by that, when rover movement was stopped, how it has measured. And this is during the LAM engine burn time. And the last one is some event, we don't know whether this event is a moon vibrating, moon crack or something, some object has fallen on moon which is captured this, still we were not sure. So this is something happened and it died down. So this is how this lunar seismic sensor has worked. And in kilometer also, it has measured the under tilt, and the rover, the movement was measured each and every time whenever it moved. So for Indian nano satellite bus area, already people are talking so much about this. Now, as ISRO, we also planning to come from small satellite to medium satellite, and their Starlink now has made so many 7,800 satellites they have flew. The number of satellites, because instead of making a big one satellite, it's small, then combine that performance, get that. So production is possible. So no need to repeat anything. So so everybody is thinking that line. So now you people will be finally using. So when you want to produce, why you want to spend more money? So use a commercial component, use the minions and things. Suppose if you use the commercial component, what is the best thing? Risk is involved. So how to reduce the risk? So there are events which we have also known. We have some devices, some things which we knowingly we have put, which is very sensitive, and we have used a single event upset protection circuit itself we have put. Sometimes if error occurs, error detection and correction circuits also we have put, some latcher protection circuits. So all these possibilities are available. So using this type of technologies, we can surely use it. So this is, I wanted to finish with this. We'll have a question answer session, and these two I just wanted to tell you, let us keep our India clean, not only here, even in space also a lot of debris is there, but we have to. Forum is open for questions. You don't want to ask questions, huh? I think ma'am is going to ask questions. See, students are not asking.
Good evening, ma'am.
Good evening.
I'm Dr. Ramuda, professor from EC department.
Yes, ma'am.
What is the role of FPGA or SOC in the sensor?
See, actually I didn't put the full block diagram where you take road processing, pitch processing. So I have from electrical signal I have converted into digital. But I need to measure with respect to my center signal whether it is what distance it is there. So I have to use a counter. So to count it and then tell what is my roll signal, and whether I have to do up counting or down counting, then whether really at the presence is come, that only my sensor signal has come or not. So all these things I have to verify it with the at presence bit. I have to check. Then use these operations to generate the roll error, pitch error, plus what is the direction of the error, whether positive error or negative error. All these operations, these counter operations, and if suppose while scanning, I have seen what is space to earth to space. Suppose sun has come in between, it will give one more spike. Then I have to ensure whether if I am seeing one more object, whether to take that scan or not. Then I should avoid that scan. Then take the next cycle. So some cycle, the same update will continue. So one more cycle it will wait. So So all these operations are done with clock precision, and with the clock precision, when I am rotating 360 degree, we have how we are generating is again your pattern things are available with IR LED and detectors. We generate clock signal. With that clock and our FPGA, we normally use a system quartz crystal clock. Use the further resolution so that the counting wise I can count with reference to my center clock. See, anything I have to reference it. So use that reference, and then when I generated all this data, I have to give this signal with a handshake signal to control system. So again, handshake also, I am started my measurement at this point to this point. This is the time roll error. From this point, if I am continuing with the same thing, without any update also, I should inform control system that I have not updated. Normally, control system person also will put a filter. I am giving update faster also. They will put a filter ensuring, okay, same update is continuously coming. Then the filter converges, then only it is putting into closed loop. So that all these closed loop things, handshake things, suppose data command if it comes, suppose some heater enable disable command, I have to operate it. All these operation I am putting it in my FPGA. So my hardware things are becoming simpler because data command I can send it through 1553. So 1553 has become a universal thing for us. Using that, whether it's a data command to which subsystem, everything is already streamlined because everybody is given one address, 1553 address. So use that, send the command. So based on the data command, I will be doing some operation. Suppose if I have sent like an extra sun presence bit has come, that data they should not take. So I will be sending a data bit saying that yes, one extra bit has come, it's a sun presence bit, so don't take this data. But still, I am giving my measurement with respect to the previous, I am leaving this measurement. So that input also we give it to them. So all these digital operations are done in FPGA. Video processing. Video processor itself I am putting in FPGA for start sensor. So the sensor head operation, everything in FPGA. What FPGA processed and giving the digital output is further attitude, determination, quaternion, compilation, everything is done by microprocessor. Microprocessor means our ERC32, 1850 ADA process. Not normal our mobile process we cannot use because this system should work reliably. So we use different versions of processors. And for all these tan equations, inverse tan, everything we are implementing in FPGA. Sun sensor, the angle measurement itself is called tan equations only. Card diagram. Please card diagram. I think students are not interested to ask questions. Fully understood or fully slept. I can take 1 or 0 like a digital bit. Either fully understood or not understood anything. So the higher level or what I explained. I have not gone to the inside electronics part because again I will be putting a block only and telling because I cannot put the circuit and explain to you how it is done. Okay, like orally only I can tell what ma'am has asked. And we have there a lot of criticalities like pre-amplifiers, the detector portion, electronics and that sensitivity. If any pickup or anything comes, it's very, very difficult. So we normally put it like an EMI gauge, isolated with respect to the other mechanical housing by grounding it separately because the motor which is running itself can give the pickup things for a monitor sensor. So a lot of EMI things we take care. Okay, thank you so much.
Close பண்ணிடலாமா?
started off with the basics of sensors, the difference between sensor and transducers, lot of characteristics of sensors, and so many other things that you had covered. It was a great portion of knowledge for us. Thank you so much. In spite of your health and various other conditions, you had, you were willing to accept our invitation and took time and effort to come over here. We really appreciate your efforts and thanks for your knowledge sharing. Now I request our HOD Dr. Jayalakshmi to present the vote of thanks.
Good evening to honorable present here. At the outset, I would like to express our heartfelt gratitude to our respected Chancellor, Dr. A.C. Shanmugam, and our Honorable President, Engineer A.C.S. Arun Kumar, for their constant support and encouragement in all our endeavors. It is indeed a privilege to extend our sincere thanks to our distinguished speaker of the day, Dr. Kalpana Arvind, retired Associate Director, Laboratory for Electro-Optics Systems, ISRO, BENGALURU, for gracing this occasion with her presence. We are deeply honored by the insights she has shared on satellite sensors and space exploration, which have truly inspired both our students and faculty. We are grateful to you, Madam, for the valuable time you have devoted to us and for igniting a passion for space technology in the minds of our young learners. Your presence has indeed made this technology talk a memorable one. A special word of thanks goes to our respected Rector, Dr. V. Vishwanathan, for inviting such an eminent resource person and for his constant motivation that drives our students to achieve excellence. Your leadership continues to shape and strengthen our academic journey. Thank you, sir. Finally, a sincere appreciation to all the faculty members, participants and organizers whose dedicated efforts have made today's event a remarkable success. We look forward to many more such enlightening sessions. Thank you all.
I request our students of our department to kindly stay for a few minutes.